So this is sort of the basic summary of the sort of standard canonical gamma ray burst picture, and Sylvia described sort of all these aspects in great detail already this morning, so I won't point out too many details here, mentioning that essentially in this sort of canonical picture we have some sort of central engine that produces some jetted outflow. So as Sylvia described, there's a lot of observational evidence actually gamma ray bursts, both long and short, actually are not sort of spherical explosions, at least at early times, but are actually confined to some sort of opening angle. So we talk about some jetted outflow that then sort of gradually decelerates into the interstellar medium, and thereby acquiring sweeping up mass, sweeping up sort of losing momentum and slowing down, and thereby creating afterglow emission on length scales that are much, much longer than sort of the typical engine length scale. So I'm going to talk about theory of afterglows tomorrow and on Thursday. So how these blast waves actually give rise to synchrotron emission, and how we get a synchrotron spectrum out of these explosions, and how that actually sort of models or describes the afterglow data we have on gamma ray bursts. But for this afternoon, I'm going to focus on the central engine, which sort of is widely believed to be a black hole surrounded by some accretion disk, and that this accretion sort of drives a jet. And the question then is, of course, where does the energy come from? So what are the physical processes that actually give rise to launching such a jet? Well, in principle, so while this is sort of more the canonical idea, there's also, of course, alternative ideas of what can actually power a short gamma ray burst. And Sylvia also mentioned this morning. So there can be also millisecond magnetars, so very strongly magnetized, rapidly rotating neutron stars. They rotate on orbital periods of milliseconds. And they have been proposed already a long time ago, actually, to power GRBs. And indeed, if you look at the rotational energy of such an object, so somehow the energy has to come from the rotational energy of this object. And if you just write down essentially a basic estimation of how much rotational energy such an object has, you end up with an energy scale that is on the order of 10 to the 52 erg. So in principle, there's enough energy. So if you compare this to the sort of total energy that that gamma ray bursts, long gamma ray bursts, and also short gamma ray bursts emit both in gamma rays, but also in sort of as the kinetic energies contained in the blast wave itself, you find that essentially you can, in principle, only if you extract a fraction of this energy, you could still accommodate most of the gamma ray bursts that are observationally detected. So in principle, there's enough energy there. The question is, how do you actually extract it? Well, the idea in this sort of magnetar model is that this sort of rapidly rotating neutron star comes with a strong magnetic field, and initially the neutron star, because in these scenarios it's believed to come from a core collapse of a very massive rotating star, the so-called collapsar. These neutron stars are hot and radiate a lot of neutrinos, and as I mentioned yesterday, these neutrinos will launch thermal winds, so there's a lot of actually baryonic material that sort of pollutes the environment. But at some point, the neutron star will have cooled down on a timescale of typically a second, which is the Kelvin-Helmholtz cooling timescale for such objects, and so the neutrino emission will stop, and at some point, the magnetic fields can dominate, so the magnetic field energy can actually dominate the fluid energy density. So essentially rho c squared, and then material could sort of slide along the magnetic field lines, and you could, in principle, power a magnetically sort of driven outflow that, depending on other confinement processes, like whether sort of the environment somehow confines this wind or not, can then, in principle, give rise to some sort of jetted emission. However, sort of the leading paradigm to power these jets are, as I already mentioned, black holes surrounded by some sort of accretion disk that again form in these collapsars. Sylvia told you about the sort of general idea of how long gamma ray bursts arise, namely as sort of the explosions at the sort of collapse of this rapidly rotating massive objects, massive stars. Also in binary neutron star mergers, as we discussed yesterday, and also as Sylvia showed this morning, you can end up with a black hole as the final remnant surrounded by some accretion disk. So these are typical systems you would expect both to be present in the astrophysical scenarios of a long burst, but also in a short burst. Now, if you look at the energy that we have available in this scenario, if you just roughly estimate the rotational energy of such a black hole of typical mass, say of sort of 4 solar masses for a long gamma ray burst in this case, so for a collapsar, of course in the short burst scenario it'll be a little less. Then you have an actually fairly huge energy scale of 10 to the 54 erg, and so even if you only manage to extract a tiny fraction of that energy, you can still power and explain sort of all the energetics of long and short gamma ray bursts. Say again? Yeah, so this is a function. So sorry, this is a function that's a function of a. I didn't write it down because the details essentially don't matter for now for the sake of the argument. But it's actually a function of a, and I just scaled this function in this case to a typical value of 0.9, so a very rapidly rotating black hole. But even if you lower this, you'd have enough energy to power both long or short gamma ray bursts. So there's also other theoretical reasons why maybe these magnetar models can't explain the full sort of population of GRBs. And so in the following, I'm really going to focus on this black hole scenario, also because it's quite useful in other contexts of astrophysics, for example, in the context of AGNs and these kind of things. So blazars and AGNs, we also think they are powered by rapidly rotating black holes surrounded by some accretion disks. The big question here really is, how can we actually extract that energy? So where does this energy actually come from? How can we tap these huge reservoirs of rotational energy? And that leads me to discuss the so-called Blandford-Snag mechanism. The idea of how to extract this rotational energy has been actually put forward back in the 70s by Blandford, by a seminal paper by Blandford and Snag. And so I thought since there's like many applications of the Blandford-Snag mechanism in all sorts of fields of astrophysics, I thought it'd be useful to go through some of sort of the fundamentals of this process just to understand this concept of how to extract energy from a black hole. This also has nice applications to numerical simulations, and this is why I will go through this in quite some detail so that we can then sort of have an understanding from the ground up for numerical simulations, trying to test this and trying to see whether or not we can actually activate such a Blandford-Snag mechanism in real astrophysical scenarios, meaning in neutron star mergers or in collapsar scenarios. And I'll show you some numerical results at the end, but let's first discuss the mechanism itself in some detail. By the way, I've actually written up some lecture notes, and they are now actually linked on the webpage. So in case any one of you is interested in going through some of the calculations, some of the math of yesterday or today or tomorrow and Thursday, you're welcome to download those and read through them. All right, let's get started. So we're looking at a rotating black hole, and so I'm going to use the Kerr metric in the so-called Boyer-Lindquist coordinate. So probably many of you, or some of you, may not have seen this before. In case you haven't seen this before, don't worry too much. Most of these details here actually don't really matter for the general discussion afterwards. Just to summarize, essentially the metric of a rotating black hole can be written in this form. This is the line element, and so these are sort of the details of all the sort of metric components that don't matter for now. Actually, exercises here in the notes. So for the hands-on sessions, in case you're interested to explore this a little more, you can do some like simple derivations yourself, just to get familiar a little bit with the Boyer-Lindquist coordinates. And the only important point I want to make here is essentially that if you remember the 3+1 split that you discussed last week in the numerical relativity lectures, you can identify these Boyer-Lindquist coordinates with a specific foliation of space-time. So, just as a reminder, I'm sure Sasha Husa has discussed this in quite some detail. So, for numerical relativity, what you typically do is you foliate space-time into slices, into spatial hypersurfaces that essentially arise as a level set of a function that we call time, which is just a time coordinate. And these hypersurfaces, we can define a observer that moves with a 4 velocity that equals the normal vector to these spatial hypersurfaces, and that is what we call the Illyrian Observer. And so you can then, in this sort of 3+1 composition, you can write the metric in a sort of the general form of this 3+1 split is given down here, where you have this function called labs and the shift vector called beta, and then sort of the spatial components gamma ij. And so in general, you can write the components of this metric in the form given below. So the pointer doesn't work really. I can't point at it. And so you can identify the metric in Boyer-Lindquist coordinates sort of with this general 3+1 split metric, and identify the labs, the shift, and so on, and the spatial components of the metric. And so this is the only sort of aspect that we're gonna need. We just assume we slice space-time in spatial hypersurfaces, and sort of this parametrization is essentially in the end given by alpha and this shift vector beta. These are 4 sort of independent functions that reflect essentially the diffeomorphism invariance of GR. And so this is essentially just the framework we're dealing with, and so we can, just by identifying these components, we can write down explicitly what the labs and the shift and everything is, and this is the only thing we'll actually need. So just to point out, the horizon of the black hole in Boyer-Lindquist coordinates is given by the expression up there, by R plus, which is just the mass of the black hole plus the square root of the mass squared minus a squared, where a is the, in this case, the spin parameter, the dimensionless spin parameter. And the other sort of interesting aspect to point out here is that the Kerr solution has this nice feature called ergosphere, which is essentially defined by the sort of zero of the GTT component, where sort of beta squared minus alpha squared equals 0. And the interesting aspect about this is that sort of the killing vector of that space-time associated with the time coordinate becomes actually space-like in the interior. So sort of everything is dragged into rotation within this ergosphere. And so again, this concept is not too important, but it'll appear during the discussion of the Stanford-Snag mechanism. But in case you haven't really heard about this, don't worry too much. We can also chat over coffee or during the breaks if you want more sort of background on this. So that said, let's start to actually discuss a little bit black hole electrodynamics. So how to actually electromagnetically extract energy from a black hole. Well, you probably may remember from some of your maybe advanced electromagnetism lectures, the covariant Maxwell equations given up there with the Faraday tensor and the Maxwell tensor. And we can define the electric and magnetic field in the way just written below, where we project the Faraday and the Maxwell tensor onto this 4 velocity of the Illyrian Observer. And so this electric field d mu and the magnetic field b mu, then the electric and magnetic field as measured by this Eulerian observer that is moving through the space-time foliation, always normal to these spatial hypersurfaces. And so we can also define some auxiliary fields, and this is just for sort of convenience to write down these equations in a more familiar way that I'll write down in a second. They actually don't have a physical meaning. They sort of only acquire a physical meaning at spatial infinity. You'll see this in a second. But they're useful fields to introduce because that makes the equations look actually fairly familiar with some of the electrodynamics that you know from sort of flat space-time. So this is going to be useful. The other important property of these fields is, and that's sort of an exercise if you want to get familiar a little bit more with these 3+1 split and understanding how these fields in this 3+1 split behave. This is one exercise in notes. You can actually show that all these fields are purely spatial, meaning that if you sort of take the dot product of these vectors, of these 4 vectors, with the normal, with the normal of the Eulerian observer, they all vanish, meaning that all these fields actually live in these hypersurfaces. So you can actually define like 3-dimensional vectors, D, B, and so on, that sort of only live in these spatial hypersurfaces. Associated with this metric gamma ij, which is the metric on these spatial hypersurfaces. So you can essentially then think of these vectors just as being 3 vectors, so di, where you sort of raise and lower indices just with the spatial metric. And so forth, and so on and so forth. And so doing this, we can just write down the Maxwell equations in a form that may be much more familiar, namely writing on 3 vectors, we get the Maxwell equations in the 3+1 split, and they look like Maxwell's equations as you may know them from flat space-time, but in a medium. Oops, sorry, this is the charge density. So let's denote this by rho q. So this is the divergence constraint, so the divergence of the magnetic field, so the no monopole constraint, right? This is the induction equation. So this is the equation for the electric field. And then we have sort of another dynamo equation for this auxiliary magnetic field H. So, and they should look familiar to you from basic sort of electrodynamics lectures as sort of Maxwell's equations in a medium. And for an ionized, so what we are now interested in most astrophysical systems is we are actually interested in not like just a vacuum, but in an ionized medium where essentially you have a lot of charges available, and so the electric and the magnetic susceptibilities actually vanish, and you can show that under these conditions the Faraday tensor and the Maxwell tensor are actually related by very simple relations, and just by this Levi-Civita pseudotensor. So, and one calls these relations essentially as the sort of Maxwell tensor being dual to the Faraday tensor, and vice versa. If you use these relations, you can actually write down well, okay, let's keep this for a second. You can actually write down relations. So that actually relates the magnetic and electric and magnetic field. So if you just plug this into the definitions here of E mu and H mu, you can actually show that there are relations, that the electric and magnetic fields are related in the following way. And this is actually very interesting. So one immediate conclusion from here that we can draw is that at spatial infinity, when sort of the shift goes to 0 and alpha goes to, so it's essentially at spatial infinity, the shift vanishes, the lapse goes to 1. We actually see that the electric field E equals the Eulerian, the electric field as seen by the Eulerian observer, and that also the two magnetic fields essentially equal. So, and this is how essentially these auxiliary fields E and H that we just defined up there actually get physical meaning at infinity. The other interesting observation you can make with these, what are usually called constitutive equations, is that these are exactly the equations that you get for Maxwell's equations in an anisotropic medium, and they have actually very interesting properties. These are special crystals that have actually fairly interesting sort of solid-state physics applications. Okay, and the interesting thing is here that sort of time really, so the shift vector here, for example, really makes this by anisotropic medium. Yes? K, oh yeah, that's a good question. Sorry, I didn't write this down. So K is the unit vector in time direction. So it's just essentially projected onto the first coordinate, the component. Okay, so I'll keep these constitutive relations here because we'll need them a couple of times in the following. Now, let us look at the actual what we get essentially from the evolution equations. So the equations of energy and momentum conservation for these electric and magnetic fields are given by the divergence of the energy and momentum tensor equals the F mu gamma I gamma. These are the energy momentum conservation equations for these electric and magnetic fields. And so if we assume that we're in a stationary space-time, which so Kerr is a stationary space-time, so we can essentially neglect all derivatives with respect to time. And then we get from the this equation the following. So we can write this down as a continuity equation for the energy density. Let me just write this down real quick. Times divergence of a flux, which we call the Poynting flux, equals E cross J. So this looks like the familiar Poynting equation from flat space-time, and where E is the energy density, but again has only meaning at spatial infinity, which is E dot D plus B dot H. And S is the Poynting flux. So the flux of energy, again, only with physical meaning at spatial infinity, which is E cross H. And you may remember this from electrodynamics classes. Okay, so this is just essentially the basic setup of sort of electric and magnetic fields in sort of a stationary space-time such as Kerr. Now let us actually discuss what this Blandford-Snag mechanism is about. So the idea here is that we might use electric and magnetic fields to extract rotational energy from this black hole. And let me show you how you can actually use external, so like a black hole sort of put into an external magnetic field, how you can use that scenario to extract energy from that black hole. So the Blandford-Snag mechanism. Because before we actually look at numerical simulations, trying to analyze and see what's actually, and to understand what's actually going on, we sort of have to understand some of these, the basic physics that we actually know what we're actually looking for. So let us assume, let's make 3 assumptions. One is that, again, we have a stationary space-time. We're only interested in stationary solutions, meaning that the time derivative of sort of any quantity equals 0. So we can neglect time derivatives, which simplifies actually Maxwell's equations quite a bit. The second is we assume axial symmetry. So that means essentially that all derivatives with respect to the azimuthal coordinate phi also have to vanish. And the third assumption, at least for the time being, is what we call the so-called force-free assumption, by which we mean that simply the electric and magnetic fields, so we don't have a perfect vacuum, but we assume that we have electric and magnetic fields and also charges present, positive and negative charges, and there are plenty of them. And we just assume that the energy momentum of the electric and magnetic fields are much, much higher than those of the particles, so that there's no energy and momentum transferred from the fields to the particles, or at least that is negligible. Not because the current that these particles, as they move around in space-time, would be negligible, but simply that the momentum and the energy of the electric and magnetic field by far dominate the energy budget. So essentially, you can think of this as sort of the electric and magnetic field dominating. And if you look at the, where do we have it? Actually up there. If you look at the, no, where did I write this down? If you look at here, if you look at the energy momentum conservation equation, right? The term that it exchanges energy and momentum between the particles, which are captured here by this by the current I, and the magnetic fields, which are in the energy momentum tensor, you see that in order to have this force-free condition, this right-hand side has to vanish. So the force-free condition tells us that this term F mu gamma I gamma. So this is exactly the sort of mathematical expression of this assumption. And then you can, again in this 3+1 split of space-time, plugging in these fields, you can show that this relation is equivalent to E dot j equals 0, and that rho E plus j cross B equals 0. So this is essentially the force-free assumption. Now we can immediately conclude from those two relations, if you take the dot product of this equation with the magnetic field, you can see that this term vanishes. So B dot E has to vanish simply because B is orthogonal to j cross B. And so what you get is essentially then we get the following interesting conditions, that also E dot B is 0. And if you plug this in up here, you'll also conclude that the same holds for the actual electric field as seen by the Illyrian Observer. D dot B also vanishes. Then also we know that since we assume stationarity, also the time derivatives vanish. And we see that E dot J vanishes, so that the Poynting equation just becomes divergence of S equals 0, which just means that essentially the energy flux is conserved. There's no source or sink term on the right-hand side. E dot J vanishes. So this is what we get from the force-free assumption. From the axial symmetry assumption, we get another or two more interesting relations, namely that if we set the phi derivative to 0, we can see that the curl of E has to vanish, which means that the azimuthal component of the electric field has to vanish. This is an interesting observation to make. And then if we plug this in again into this equation, into the force-free equation, we can immediately conclude that since the phi component of E vanishes, also the phi component of this cross product has to vanish. And then taking the phi component of this also has to vanish, which implies, again, that the poloidal component, so if we think of this space-time, if we think of this setup, say we have the black hole here, we have some sort of magnetic fields, say magnetic fields, right? And we decompose vectors into a poloidal and a toroidal component, meaning that the poloidal components being the sort of r and theta components. So any vector can be decomposed into this poloidal component plus some azimuthal component, which is essentially something called the toroidal component. Not quite, but roughly. And sort of this poloidal component just takes the first two components, the radius component and the theta component. And since the phi component has to vanish, it tells us that the poloidal components of the current and the poloidal component of the magnetic field actually have to be parallel, because if they wouldn't, then the cross product would actually point into the orthogonal direction, into the phi component, and actually would violate this constraint. So we know that any current that is flowing in this black hole magnetosphere, any poloidal current has to be parallel actually to the poloidal magnetic field. And that is actually a very useful relation that we'll invoke in a couple of minutes again. Okay, so should make some space. Well, okay, let's go on for a second here. So since the azimuthal component of the electric field vanishes, there exists a vector, so E phi equals 0 implies that sort of there exists a vector field which I call omega that only has a azimuthal component, such that we can always write the electric field as omega cross B. Let's put a minus sign here, just for convenience. And so we can always express the electric field as this cross product of some azimuthal vector that we call the angular velocity in a second, and the magnetic field. Now, if we plug this expression back into these constitutive equations over here, in the first one, we can actually write down a nice relation also for the corresponding electric field as observed by the Illyrian Observer. So this is just plugging in this above expression. And furthermore, we also get, if we plug this expression again back into here for a stationary spacetime, we get a nice relation also for the magnetic field. And if you just use standard identities for the curl operator of applied onto a cross product of vectors, you'll find that this equation implies that B dot the gradient of omega, where omega is essentially this component here, has to vanish. And that tells us that omega is constant along magnetic field lines. So that's an important observation, and that's why we call it the angular velocity of the magnetic field. So this will be a useful relation. Okay, so I won't go through the exact details of the math. It's actually fairly simple. I don't want to confuse you with more equations at this time. If you just use the relations that we derived here, you can actually show, and that is one exercise for the hands-on sessions if you, in case you're interested. You can show that the poloidal component of the Poynting flux, so of this vector here, if you just plug in the expressions that we derived for the electric field, you can show that the poloidal component of this Poynting vector is given by minus omega, the phi component of h, times the poloidal component of the magnetic field. So that is a very important relation that was that we were after, essentially. So the whole story here was about deriving essentially this relation. And so here you can see we can already make some important conclusions from this formula. Namely, this will in the end be, as I'll show in a second, will be the energy flux that we can actually extract from the ergosphere of the black hole. And the way this works is that we will show in a second that we've already shown that omega is constant along the magnetic field lines. So omega won't change as we go from the black hole to spatial infinity. It just stays constant along the magnetic field lines. We will show also in a couple of minutes, so this is constant along B. This is also constant along B. This is something we'll show in a second. This means that in order to extract, so if we accept for now that this will be the flux in the end that we extract from the black hole, the energy flux that we extract from the black hole, you can already see that it scales. So with these two quantities being constant, it scales with the magnitude of the poloidal magnetic field. So this tells us that essentially the idea here is if the more energy we want to extract from the black hole, the stronger this poloidal magnetic field has to be. And in astrophysical scenarios, that's exactly the challenge, how you can create a poloidal magnetic field that is sort of a large-scale structure in a stationary scenario that is strong enough to actually extract a significant amount of energy from that black hole. So why do we actually get this energy flux, and why is this actually why does this actually not vanish at infinity? Because that is sort of the question that we have to answer. While this vector may be maybe non-zero around the black hole in the immediate vicinity or so, it may be actually zero at infinity, and we may actually not be able to extract rotational energy from the black hole to infinity to put into a blast wave or something. So let me show how this actually arises. I'll have to erase some of this. Okay, I'll erase this as well. Okay, so this is sort of a new section. Well, I don't need to number it. This is what is called the electromotive force. If you want to go through all these calculations again, they are all sort of written down and sort of discussed in the notes. So the big question is how do we get a non-vanishing Poynting flux at infinity? And because we on one hand we know from what's called the no-hair theorem that essentially black holes can't sustain their own magnetic field. So if we want actually a solution of a magnetic field immersed into some of a black hole immersed into some magnetic field, that magnetic field has to come from outside, has to be provided somehow. Meaning that there have to be some charges, some currents flowing around in the magnetosphere somewhere around the black hole that actually generate magnetic fields. And the question is, how does that current, how does these charges actually come about? How do they flow, and how can they produce a magnetic field and extract energy to infinity? Let's start by just noting that in vacuum, let's assume we don't have charges, only electric and magnetic fields. In vacuum, these equations here just read the absence of charges and everything, that the curl of H and the curl of E vanish, from which, so you can write these vector fields just as gradients of some scalar fields. So let's call this psi, and E as the gradient of what is more familiar to you, the electric potential. And since we're making, again here, the assumption of axial symmetry, the derivative with respect to phi actually vanishes. So we immediately conclude that H phi equals E phi equals 0, which shows that in vacuum, actually this Poynting flux sort of vanishes, and we can't extract any energy. So it'll be a dead magnetosphere. So the sort of conjecture here is that the critical ingredient here are really charges. So we have to place charges into this magnetosphere, into these electric and magnetic fields. And so the question then is, how can we do that? And how can we do that in an astrophysical environment? Well, a fairly easy way to produce charged particles, meaning electrons and positrons in this case, is just by having very strong electric fields that can give rise to a pair creation of electrons and positrons, so-called pair cascade, and they can sort of populate this black hole magnetosphere with a lot of charges, electrons and positrons. Now, if you place a lot of charges into electric and magnetic fields, there can be an effect that is called screening. So just imagine we have a lot of, so let's say we have magnetic fields like this, right? And we just place, let's start with a electric field. So we have an electric field that is sort of externally applied, so we just assume it exists, right? And we just place a lot of charges randomly, and these are like positrons, electrons, so let's say essentially the masses are sort of negligible, and we apply this electric field, and what will happen is that these charges will separate, right? So if you just let time pass, what you'll have is a scenario in which sort of all the positive charges went to the one side. So you have all the positrons sitting up here. They are all up here, build a positron cloud, and you have all the electrons down here, right? And so what they will do is, this will induce a field that is just opposing the externally applied field, right? So you will have this sort of E field that is induced. And now imagine you have enough of these charges around, so they will separate until they totally screen this field, that the total field existing of the externally applied field plus this induced field vanishes. So actually, these charges will, it's called screen the field. So they will actually effectively make it disappear. Which means that if there are no electric fields anymore, there can't be no currents. And if there are no currents, there can't be any magnetic fields. So how can you actually sort of circumvent this problem? Because, as I said, we need some magnetic fields in order to extract energy. Okay, let's look at this electric field that we get if we place charges in such a magnetosphere. So from the basic Maxwell equation in stationary spacetimes, curl of E, and also that we know that so this is the constitutive equation. Oops, alpha plus beta cross B. So just this relation up here. Those two imply that actually the electric field is given by this term here. Oops. Beta cross B. So we see that somehow in this magnetosphere, so this is the electric field D as seen by this Illyrian Observer. So this is the actual physical electric field. And you can see that this electric field is sourced by this term, where for some reason the shift vector conspires with the magnetic field to provide a source term to this electric field. So it's really the space-time here acting that actually produces an electric field. And again, the problem, of course, is given this electric field, how can we avoid the screening of this electric field that is generated? Well, just expressing this screening sort of in more mathematical terms. We must have that the dot product of the electric field times the magnetic field vanishes, and also that the magnetic field dominates the electric field. Okay, you can just think about this the following way. Let's say you have a magnetic field, right? And also some electric field. Let's say this is actually orthogonal. So I should have actually, let's say this is the electric field. So if they are both orthogonal, and assuming that the electric field is actually weak, so that the magnitude of the magnetic field is much larger than the electric field, right? Then if you put any charges in there, they are forced to gyrate around this, around the magnetic field. So they're not free to move wherever they want. But in order to screen the field, they actually have to be free. They actually have to, sort of move must be free to move in the direction of the electric field, which they can't. So this is sort of essentially the pictorial representation, essentially, of these two conditions. Because, for example, if you'd had the opposite case where you have a magnetic field, right, and then the electric field is in the same direction, then you can actually accelerate charges along the magnetic field where they are free to move in this case, and they accelerate along the magnetic field. So you can push sort of. So if this is the electric field, you can move positrons up here, and you can move electrons down here, and they will actually then set up an induced field that screens the electric field. So this is just showing you essentially in a sketchy way, essentially what these two conditions mean. Okay, and what I'm now going to show is that, and this is a theorem by Komisarov, 2004. So in a similar way, Blanford and Snag have shown this already back in the 70s. But so he's put this on a sort of more in a sort of more modern fashion and in a more general way in this 3+1 split that we're working with right now. And what we're now going to show is that sort of you could call this a theorem if you want, namely that these two conditions, let's call them 1 and 2. So this is due to Komisarov. I believe it's 2004. 1 and 2 cannot be satisfied simultaneously. Throughout the entire magnetosphere. And just to make a long story short, I'll go through I'll sketch really briefly the proof for that, why this is. But just to give you essentially an snapshot of this is the reason why they can't be simultaneously satisfied is the presence of the ergosphere. Because of the ergosphere, both of these conditions cannot be satisfied at the same time throughout the whole magnetosphere. So we'll break these conditions, meaning that the electric field will not be screened, meaning that there is a current, so charges can move, and we'll show that this current actually will induce a magnetic field that has a non-vanishing phi component, so that we actually get a non-vanishing point flux, or non-vanishing energy extraction from the black hole at spatial infinity. And the proof goes essentially in the following way. It's fairly straightforward. Let's assume that first condition holds. So let's assume that the electric and magnetic fields are actually orthogonal. Then we know from, I've erased it already, but if you plug this into the constitutive equations, you immediately also find that E dot B vanishes. Okay, and then this is actually an exercise. If you want to look into this in a little more detail, just it's a fairly straightforward exercise. So it's just essentially algebra, just putting in some expressions. But you have to. It takes a couple of steps, so I won't do it here. If you square the equation for D over here, you can show that you get the following relation. And now rearranging terms in a way that looks similar to this, what you'll get is the following: B minus D squared alpha squared. And then you have B squared. And then you have some function that only depends on this angular velocity of the magnetic field lines. And it depends on the spatial coordinates r and theta. And then there's another term that involves, again, the angular velocity of the magnetic field lines and the shift vector and the phi component of h divided by alpha squared. So it's very simple, just squaring one equation and using that conditions. And so the interesting observation here is that now let's assume that we actually have a dead. So let's say it's actually have a dead magnetosphere, so no currents, full screening. So let's assume sort of the screening condition, the screening assumption holds. That means that this field has to vanish. So let's call the dead magnetosphere means h phi equals 0, which is also the vacuum condition here that we got, right? So we assume that the screening holds and we have a dead magnetosphere. So we only focus on this first term on the right-hand side. And the interesting observation here is that the sign that we actually care about because of this condition, the sign of this does not depend on the magnetic field strength. It just depends on some spatial coordinates and omega. And I can just write down the expression for f just in case you want, just in case you're interested. So this is f r theta is alpha squared minus omega plus beta dotted with itself. And you can see, and as we will see now, there are conditions under which the sign of this function can change, and that exactly determines whether or not the second condition actually holds, because the magnetic field doesn't have any say in this. So let's see, and let's evaluate this expression at spatial infinity. I believe we have a couple of minutes left, so I'll just quickly go through this. Okay, let's keep the screening condition. Okay, let's evaluate this at infinity, meaning that essentially we take the radius to infinity, then this function f r theta goes to 1 minus omega squared, simply because at spatial infinity alpha goes to 1 and beta goes to 0. So we're just left with 1 over omega squared. And we can rewrite this as, so just remember this is a dot product, so this is omega dotted with itself. So this involves the spatial metric. So what we get is 1 minus the azimuthal component squared, and then gamma phi phi, right? So omega, remember omega was omega times the unit vector in phi direction. So omega dotted is sort of gamma phi phi, and then we have omega phi, omega phi, and then omega phi. Wait, sorry. Okay, omega squared, and then we have gamma. Let's write this out explicitly. It's g phi phi omega squared. And then using the expression for the metric of gamma phi phi in Boyer-Lindquist coordinates that I've shown you up there some time ago. So if you plug in gamma phi phi in here, again evaluated at spatial infinity, you get that this is simply 1 minus omega squared r squared sine squared phi. Now, as r goes to infinity, clearly f becomes negative at some point. So the only way you can prevent this function from getting negative is to set omega to 0, meaning that the magnetic field doesn't rotate. You just set the angular velocity of the magnetic fields to 0. Now, this again implies that if we take this back into the general expression for this function, if omega vanishes, we're just left with alpha squared minus beta squared. So this means that f is just given in general essentially by alpha squared minus squared. And now if you compare this to the condition of the ergosphere that I've written on the slides up there of GTT, you'll see that this expression becomes actually negative inside the ergosphere. So it's positive outside, but precisely because of the existence of the ergosphere, it actually changes sign, which tells us, and that essentially concludes the proof. So negative inside ergosphere, and sort of that essentially concludes the proof, telling us that this condition cannot be satisfied everywhere, precisely because of the existence of the ergosphere. Okay, since we assumed that in this derivation here that h phi is 0, we conclude that actually h phi does not vanish. There has to be some azimuthal component of this field. Now, let's go back to this equation and see how this how this component of the magnetic field actually requires a current to flow. So let's take again the basic Maxwell equation here for a stationary spacetime. So curl of H equals the current J. And now if the azimuthal component of H is not 0, then it follows that there exists a poloidal current J poloidal, and that's the important conclusion from this theorem essentially. And as we've shown earlier, the poloidal component of a current has to be parallel to the poloidal component of the magnetic field. So we know if there is a poloidal current, we know that the poloidal current has to be parallel to the poloidal magnetic field. That's what we showed earlier. So if we know there is a poloidal current, it has to be parallel to the magnetic field. And it's exactly precisely this poloidal current that generates the azimuthal component of the magnetic field. And that in turn tells us that there's a non-vanishing azimuthal component of this magnetic field, which is another condition. I don't have the time to derive this now because time is up already. But you can show that this H phi is actually also conserved along magnetic field lines. So you can also show that B dot so let's well, we should write this out. So that essentially BR dr HR plus B theta d theta H theta actually vanishes. So and so the point is that the azimuthal component of H is conserved along the poloidal magnetic field lines. Omega, as we've shown, is conserved along the poloidal magnetic field lines. We've shown that there has to be current, Jp, that drives this H phi not being 0. And that induces the poloidal magnetic field. So there is actually a non-vanishing Poynting flux that takes energy from the black hole, from within the ergosphere of the black hole, to in spatial infinity. So this tells us that we somehow have to put the black hole into an external magnetic field that has some sort of large-scale structure. We let it relax and settle it down to a stationary magnetosphere. And if then essentially the conditions of axial symmetry and stationarity and also the force-free condition are roughly sort of satisfied, then we'll actually extract magnetic energy from rotational energy from the black hole, and that energy flows along the poloidal magnetic field line. So when we look at simulations, what we need to identify is, like in an astrophysical context, whether or not the system develops some large-scale poloidal magnetic field lines, because that's really what we need in order to let energy essentially flow from within the ergosphere to spatial infinity. And I'll show you the simulation part in tomorrow's lecture. I didn't, so I ran a little late on this, and so we'll do this tomorrow. All right. Are there any questions for the coffee break, or? Sure. Yeah. Yes. Yeah. Right. Yeah. Yeah, that's a good question. So in practice, actually, you only what we are going to extract. So at least in an astrophysical scenario, the magnetic fields would need to be unphysically high to actually extract a significant amount of rotational energy from the black hole. So sort of in practice, this actually is not a problem at all, because you'd really need a sort of a fairly extreme magnetic field strengths, where then sort of other physics kick in that sort of prevent these strong magnetic fields. But in principle, yes. So the black hole loses rotational energy over time.
Maybe the common is the pulsar. Brand new pulsars, they have their highest magnetic field, so those break because of that. But once their magnetic field gets to be sufficiently low, then it takes the time scale for further slowing down the pulsar is just too long for it to matter. So in the black hole, you're on that regime.
Yes. Of the fields, so yeah, that depends on the. So I'll show this actually in the when I talk about the simulations tomorrow. But sort of typical magnetic field strengths. So you can do some order of magnitude estimates from these formula here, just to get an idea of like how strong the magnetic fields needs to be in order to explain energy extraction on the level of GRBs, meaning long or short GRBs. So something like 10 to the 51 or 10 to the 50 erg. So it turns out that under sort of reasonable astrophysical assumptions, you typically need something the order of 10 to the 15 Gauss or so in magnetic field strength, in the poloidal magnetic field strength, to extract those. And sort of the big practical problem in astrophysical applications is then how do you generate these strong magnetic fields? And that is something that we'll discuss in the context of the simulation tomorrow. All right, then let's have coffee.